although I guess I knew all the results that Dick has been talking about that Dennis proved in the subject, I never really thought of them all together and how much you did and what was a relatively brief period of time. Again, really a great honor to speak on this occasion. I also wanted to address Misha's quiz from yesterday. Felt that needed to be done. So I wanted to look at, let's see, so we can look at some way of making this go on. So can we see this, or should I zoom up the, maybe don't go out. Let's see if I can figure out how to do this. That was too big. Okay, so what I'm going to talk about today is the lower left-hand corner of this scorecard, and I guess I just wanted to notice a couple things. One, it's sort of interesting how, although there's this dictionary between rational maps and Kleinian groups, often one thing is, it's easier to prove one thing in one side of the dictionary than it is the other. So we have this sort of diagonal where structural stability implies hyperbolicity was known for Kleinian groups first, and on the other hand, structural stability is open and dense was done for rational maps before it was first. So they had this sort of opposite behavior. The other thing I wanted to point out is, well, on the rational map side, well, this paper is what, 25 years old or so. I mean, it was verified numerically, and yet still, we had nothing, right? I guess, but the rational map side was verified numerically, and yet still, they're still working. So I don't know how that helps answer Misha's quiz, but well. Okay, so the other thing I was thinking about is that there is this paper, famous paper of Thurston, where he discusses. At the end, he gives many questions. So there's still quite a few questions that we can think about for hyperbolic geometry. And I thought, well, let's look at this list that Thurston put up in 1981. And actually, as I started looking at it, I realized actually we really have done a pretty good job. So you can go through these questions, and so well, the 1 and 2 are Perlman's work. 3 is the orbifold theorem. 4 is a little ambiguous what exactly it means, but I think we have a much better idea of what hyperbolic phase surgery is than we did 30 years ago, and so on. So the various questions, the tameness conjecture, the density conjecture, and so on that we all know. And then as you go a little further into the next page, well, some of these are known. So if you get to 15, 16, and 17, these are still unknown. This is and 18, these are the virtual Hawk conjecture and the fibration conjecture. So there's been some recent progress on this, though, actually by Jeremy Kahn and Vlad Markovich, that gives sort of a partial solution to this question about whether, or part of the way to a solution of whether this virtual Hawk is true. And well, I can't, help but observe that Jeremy normally does holomorphic dynamics, and so I guess he thought that he would come over here where the questions are supposedly easier, but like many things in holomorphic dynamics, they can only come up with only get partway there. And they used, well, anyway, it's a great result. What they did is really fantastic. But actually, as I was looking at this I thought was pretty interesting. Before this question, if you look at this last paragraph, what Thurston wrote, the paragraph there, Kleinian groups are very beautiful and rich with an amazing variety of productive ways to think about them. And then he mentions this article of Bers and Dennis for 2 different points of views. And I think this is one of the reasons that we've had more success in Kleinian groups, is there are so many different ways, so many different methods you can use to attack them, and that makes it easier to prove things. But then I like the last sentence. Perhaps by the year 2000, our understanding of 3 manifolds and Kleinian groups will be solid, and the phenomenon we now expect to be proven. So it's 2011, and I guess we've done a pretty good job on this Thurston's question, and I think there's lots of new things to think about too. Okay, so that's all I need of the screen. Let me pull that up. All right, so I wanted to start my talk proper, and I wanted to start off with sort of a little warm-up problem. And so what do we want to prove? We want to prove that every Kleinian group is a limit of convex co-compact Kleinian group. So let's do a little exercise in the Fuchsian case, and I want to look at the Kleinian group generated. So the group generated by the parabolic transformation, z goes to z plus 1. So what does the corresponding surface look like? So instead of a 3-manifold, we're going to think of this as just a surface. Well, it's going to be a cusp. Okay, so that's not a convex co-compact hyperbolic surface, right? If I took, well, there's the convex core of this. It doesn't. This is an elementary group. So if you define the convex core the way you dictate it, it doesn't really work. But there is sort of like there's no compact convex subset of this where the inclusion is a homotopy equivalent. So this is not a convex co-compact group. But we can do a little construction to make it look convex co-compact, and here's how this is going to work. I'm going to take, say, a point on this cusp, and I'll take an arc that goes off to infinity. Maybe I should have drawn it a little more room here. Okay, and what I want to do is I want to cut this cusp open and I want to glue something in. And what I'm going to glue in is I'm going to take a copy of the hyperbolic plane, and I can think of this copy of the hyperbolic plane as being the universal cover of this cusp, and I can lift up this arc, or one copy of this arc, upstairs. And then what I'm going to do is I'm going to cut, so I'll cut in two places, here and here. And when I do that, and then I'll glue crosswise. Okay, so I'll get a new. Okay, so this is this piece here that I've glued in. And now when I do this, what I get is I get a hyperbolic surface with a cone point, so of cone angle 4 pi. Okay, so here's the exercise. The exercise is, well, we want to prove that this cusp is approximated by convex co-compactness. And this cone surface, this is going to be convex co-compact. Well, it's not really a Kleinian group, it's not really even a Fuchsian group anymore, but it's going to have a compact convex core. So if because I glued it in the surface, I made it wider, and now I have a convex surface facing up, and then I have an original convex surface facing down, and so I have this nice convex compact core. The problem is I have this cone singularity. Okay, so this is supposed to give us an approximation for my original cusp, and as I let this cone point go further and further out the cusp, the approximation should get better and better. So this should give me a way of approximating this original cusp by something that's convex co-compact. The only problem is I need to resolve this cone singularity. I need to get rid of it, so I need to do something to get rid of that. Okay, so this is a very difficult way of proving what's really a pretty trivial theorem. It's not too hard to see directly just by knowing what PSL2C looks like, that this thing can be approximated by convex co-compactness. But this idea will come back later.
Is there a general result that can diffuse the negative curvature out and let it become constant and then rescale it?
Is there a general result? So like in this particular case, I don't think it's... Oh, like, so just if you had a smooth negatively curved surface?
Yeah, just let it go out.
I'm not sure. Maybe, I don't know if anyone, like, I think maybe in the two-dimensional case, they know that the Ricci flow would work, but, or I guess, yeah, something like Ricci flow would work, but I'm not really sure. Okay, so, let's restate the conjecture, and then I want to, we have to have a workout. All right, so let's restate the conjecture. So so this is the original conjecture. And what the statement is that every finitely generated finite group is an algebraic limit of convex co-compact finite groups. And just to so Dick went through all this, but just to give sort of a brief reminder in sort of a more direct, concrete way of what this means. So what do we have? We have some finite group rho. So this is a representation of some abstract group into PSL2C that is discrete and faithful. And then what we want is we want some rho I finite groups, again, from G into PSL2C, with rho I convex co-compact. And we want that rho I of G converges to rho of G for all G in the group.
So you don't require the rho I or faithful?
Discrete faithful, yeah. The rho, yeah, by definition, everything is discrete and faithful.
But what if the original group has parabolics, rank 2 cusp?
Oh, thank you. I want to ignore the existence of parabolics just to make things easier. But no, the statement is still fine. It's just, I mean, you might make a stronger statement that you always want to find a type-preserving geometrically finite group, but I mean that statement still makes sense even.
But they won't be convex co-compact.
Well, for instance, if you had a yeah, the statement still makes sense, right? So let's say you had something in age, you had a surface group with a cusp. You could approximate it by Schottky groups, right?
What if the rank 2 cusp?
Oh, the rank 2 cusp. If the rank 2 cusp. Oh, okay, that's what I meant to say. Yeah, that's what I'm going to stick with what I meant to say at the start. Let's forget that they're any cusp, because that's just going to be an easy.
Say without rank 2 cusp, do they formal?
Yeah, okay. So,
Without rank 2.
without rank 2 cusp, let's, for every finally generated finite group, yeah, without rank 2 cusp.
Right, so, I mean, we're saying that this question, called a question, is like a question in dynamics, whether if they're classified as persistent, whether they can be approximated by hyperbolic persistence, which was the main question in the 60s, failed school earlier. So this is the natural, but that's not true in general. Sometimes it's true. So it's like, even here you have to, let's do it pointing out, have to be in the circle. And then it becomes true. It's very easy for it not to be true.
Okay, so I want to discuss the proof of, two proofs of this conjecture. One I'm just going to talk about very briefly, and then one I'll talk about in more detail. So there are two proofs. So one uses the, one involves the anti-lamination conjecture, and the other involves, uses, let's say, a technique called grafting, and also hyperbolic cone-manifolds. Okay, so I'll briefly outline how you go from the anti-lamination conjecture to the density theorem, and then I'll talk in more detail about the grafting version of the proof. And this is what I was my little example here sort of corresponds to this second version. Okay, so proof one. There are 3 steps. So step one, Dick and Dave talked about this yesterday. So what we want to do is we want to associate to every Kleinian group. Well, so first of all, if we have rho, we can build a 3-manifold by taking the quotient of hyperbolic 3 space by the group. And so by tameness, M rho is equal to the interior of some manifold n where n is a compact with boundary. Okay, so this theorem was proved by, as Dave discussed yesterday, this is the tameness theorem of Agol and Calgary combined. Okay, now once you have this tameness, you can associate end invariance.
You attach the names to the last version, the person previous to the last step.
I was gonna bring up the other people's names in it. In this.
Such a long set of ideas.
Yeah. I was gonna bring up the other names in this part of the set. So I'm going to associate end invariance to each component of the boundary of n. Okay, so these two things are really very connected. And so the names I'm going to mention here are Thurston, Monahan, and Canary. And so the first version of this tameness theorem, well, the geometrically finite version of this tameness theorem, maybe what's even Martin up here, was due to Martin. And then in this case, when the manifold is no longer convex compact or is no longer geometrically finite, the first version of this tameness theorem was due to Thurston and then Monahan and then. So as part of this construction of tameness, they also what Thurston produces is what's called an ending lamination. And I'm not going to define this ending lamination. I'll say a little bit about it later. But the tool you use to construct the ending lamination is very much related to the tool you use to show that the manifold is tame. So in particular, as Dave talked about, you have these closed curves going out the end of the manifold. And you sort of use those closed curves to produce tameness, and you also use those closed curves to produce the ending lamination. And then Canary showed how you can associate, once you know tameness, how you can associate one of these end invariants to the manifold.
So who takes care of the step of the end not being injected from 5-1? That's Canary?
Let's see. So to get the end, if you know tameness and you want to get end invariance, if you have a manifold that you know is tame and you want to get end invariance, and it's not compressed and it's not incompressible, then that's tame. Okay, so that's step one. We associate this set of invariants to our Kleinian group. So step two, is to show for all for a given allowable set of invariants, n invariants, there exists convex co-compact rho sub I with rho sub I limiting to some rho prime, and rho prime having the given end invariance. Okay, so the proof of this step also has a quite involved history, and I really, so we've been talking about these three conjectures for the last few days, the density conjecture, the tameness conjecture, and the anti-lamination conjecture. The existence of these limits was sort of another big conjecture in finding groups that really could also be included, I think, among those three. And so the original limiting theorem was probably the double limit theorem of Thurston. And this is in the case when you have this is in the case when you're looking at just limits of quasi-Fuchsian groups or surface groups. And then there's been a lot of generalization. So Thurston proved, he proved various theorems about when limits of Kleinian groups exist, and this is really important in his construction, in his hyperbolization theorem. So I could write, there's various versions that Thurston proved. Another big important result was there's sort of a limit theorem in the compressible case by Kleinian and Soto using. So this proof used sort of techniques developed by Attal to prove the double limit theorem. So Attal gave another proof of the double limit theorem, and that's what Kleinian and Soto used to prove this limit theorem in the compressible case. And well, to get everything we need to prove the density conjecture, so that there's other names that should be mentioned, I guess. Queer, Oshika, and Matzis. So I think one of the reasons this conjecture isn't as well known is it's much harder to state exactly what you need here. But in any case, there's a lot of really important work in this step too. Okay, and what's the final step? Well, the final step is what Yair is going to talk about tomorrow. And this is called the anti-lamination conjecture. And the anti-lamination conjecture says that a Kleinian group is uniquely determined by its end invariance. Okay, so this was proved by Brock, Canary, and Minsky, sort of finishing a program with Minsky and using important work of Maser-Minsky. Okay, so let's see how this all fits together. So what do we know? So step 3 implies that rho equals rho prime. So that gives us the density conjecture. Okay. By the way, when did I start? 9:40. Okay. All right. So what I want to talk next is about this other proof using grafting and hyperbolic cone-manifolds. Okay, so the proof here is work I did with Suto and also work I did with Brock. And what I want to talk about is a special case that I guess I did originally. Historically, which, oh, these two? Oh, it didn't come first. It's never, so, I don't want to answer that question. There's been some issues about writing this whole thing down. So, in both proofs, this second step comes up. To finish both these proofs, to finish off the whole thing, there's issues that come up in the second step and the same sort of issue was needed in both cases to finish it off. So, okay, so I want to first do a topological construction. So before I Okay, so now let's just think of M as being a manifold, and it's just a simple manifold, S cross R, where S is a closed surface. And, well, it's not really that important for the topological construction, but let's just assume that the genus is bigger than 2 for later. And then gamma is a simple closed, is some central simple closed curve. And, okay, so what do we want to do? I want to take these two ingredients, and well, one more ingredient. So let's take an annulus by just taking that simple closed curve and prolonging it, by crossing it with, so this sits inside of M. All right, so I want to mimic the construction that I did over there in the two-dimensional case. So we have a bit more topology, so it's slightly more complicated. So I also want to let W be the cover.
Looks like now they're saying the co-dimension 1 part,
It's going to be almost exactly analogous. It's just slightly more complicated because a curve has some topology that a point. So I want W to be the cover of M, corresponding to pi 1 of A. So what does this look like? So W is, it's a solid torus, so let's write it as a disk cross S1, and then we can lift A homeomorphically to some A tilde sitting inside W. Okay, so this is A tilde. And then what are we going to do is, just as we did over there, so now I want to cut.
That's only two-dimensional, so what's the real thing right there?
What's only two-dimensional? Oh, no, I didn't want to fill in. This is a disk. Cross S1. So it's three-dimensional. Yeah. I just didn't want to fill it in because then I wouldn't be able to draw my A. Yeah, that's a
I
solid.
thought it was a disk, but I had it in mind that wrong.
Yeah. You're only off by 1. So we cut M along A, and W
just the essential component?
No, I want to lift a homeomorphically, so just the homomorphic.
But there's many other preimages, right?
Yeah.
Like over there.
Right, there'll be many over there too. Right. Okay, so what's the picture? So here's the topological picture is just, we've cut M open, and we've cut W open, and now I'm just going to glue crosswise. Now notice there's a covering map from W to M. And I can use that covering map, and there's also the identity map from M to M. So I can use those two maps to define sort of a branch covering map from, let's call this new glued manifold, the union M sub gamma. I can use these two maps to define a map from M gamma to M. So along the W part, this is just the covering map. And along the M part of M gamma, this is just the identity map.
M gamma is what?
M gamma is what happens when I glue these two things together.
So what's the statement about something's a cover? You proved it. What's the statement?
Yeah. So what I want to say is, so pi gamma is a local homeomorphism, except along gamma, where it is a branch double cover.
Getting the analog over there.
Yeah, exactly analog. What's happening over there?
What is pi gamma now? I'm ready for pi gamma. What's the
So pi gamma is the map from M gamma to M. So pi gamma restricted to W, this is the covering map for W. And pi gamma restricted to M, or maybe I should say W minus A tilde. And pi gamma restricted to N, this is just the identity map. Okay, and
So it's an irregular branch cover.
yes, I think that's the correct terminology. Yeah. So it looks like a covering map in most places except around this curve where it's a branch double cover. But yeah, I guess it's irregular because there'll be points there that hit the branching locus that aren't branched. Okay, but it's a proper map. It's a nice map. Away from that. It looks like a covering map away from this point. Okay. All right, so now let's add a bit of hyperbolic geometry into this. So if we can take this picture, this topological construction, and we can apply it to a hyperbolic structure on the manifold. Ooh, that doesn't sound good. A little over.
The long one.
The big one, yeah.
Oh,
It has
Two
two
sides.
sides.
this is the bad side.
Yes.
Interesting.
And this is a good one.
It makes sense, you know,
Really?
yes. You didn't have
The left side of the board is erased.
I mean, in my defense, in most erasers, the part that's black is the side you use. Okay, so now let's take this as a proposition. So what I want to do is I want to assume that so if M hyperbolic structure. And again, I want to ignore cusps, so let's say without cusps. Then the pulled back metric and gamma. Oops. I need to make one other. Oops, I forgot one other assumption. And gamma cross 0 is a geodesic. So gamma cross 0, right? That was the boundary of our annulus sitting inside M. Then the pulled back metric is a hyperbolic cone metric. And okay, so this new manifold is homeomorphic to S cross R, just like the old one was. And there's one end, this top end I'm going to call the grafted end of the new manifold. The bottom end is exactly the same as the bottom end of the original manifold, but this top grafted end has changed. And the important fact is, and the grafted end is geometrically finite. Oh, so I still have my picture here. Yeah, so just like in this two-dimensional case, when I insert this big wedge that turns my cusp into something with a flaring end. And the same thing is going to happen in this three-dimensional case.
So you didn't bother saying that one was finite because all six things are or something.
Oh, this was geometry?
Yeah.
Yeah, I guess I'm using bad terminology. So,
No, I just wondered why you didn't say it.
oh yeah, this is geometrically finite, right. So, I mean, there is no geometrically infinite finite, so the analogy isn't perfect, but.
Could you say the grafted end is convex co-compact?
You could, but it sort of doesn't make, I mean, convex, I don't know. It's sort of bad, there's no good, I don't know. Maybe you should use the word as a convex end or something.
I mean, in dimension two, like, it's no big deal that you get something geometrically finite because everything is like that, but in dimension three, that's.
Oh, I'm going to say what? I'm going to say a word why that's true. Yeah. Oh. I wanted to say something about the. Yeah. Okay. Well, so let's give a little sketch of the proof of this. So. We'll view it by contradiction. So let's assume not. Now, by the topological construction, we have tameness. I mean, this new manifold we have is, just by construction, it's going to be homeomorphic to S cross R. And once you have tameness, you can get geometric tameness. So in particular, there exist bounded, if this is the case, then there exist bounded closed geodesics, bounded length closed geodesics exiting the end. Okay, so this is really a combination of an argument of Bonahan using and to make it work in this singular case, we need to use some work of Bowditch. Okay, and how is that helpful? So let's imagine what would happen if we have all these closed geodesics. So here we are in M gamma. Yes?
So, this is different somehow from what Canary did, and there also you have a friend.
What's the question?
Is this different from what Dick did in his thesis? So,
I mean, just the vote, I mean, this.
yeah. So when we wrote this down many years ago, we thought very hard about what exactly we needed to use. And if I remember, I'm pretty sure that what Dick did wasn't quite enough. So yeah, I should say, I mean, so.
My thesis, I deserialize and then apply things. This is different.
But yeah. So, well, let me say this. So this construction happened when I was a postdoc at Michigan, and that's not a coincidence. So this idea is very similar to Dick's trick for going from compressibility to incompressibility.
What's the reference to voltage for?
So the reference to voltage for is, you need to know, okay, so if it's not convex co-compact, let me see if I remember this correctly. So you want to know that, yeah, so you want to know something like, if all the geodesics, all the closed geodesics are contained in a compact set, then it has to be convex co-compact. So if it's not convex co-compact, whatever that means in the singular setting, then you have to have geodesics going out the end, but then you want to go from having geodesics going out the end to having bounded geodesics going out the end. And that's, I guess I would associate that to Bonahan, although now probably the best way to do this is to use the shrink wrapping that Dave mentioned yesterday. So,
Can you just say what geometrically finite means in this cone setting?
yes, that's a good point. Well, maybe I'll say it as we prove. Okay, so we have these geodesics going out the end, and then we can look at what the image. So now we can map those geodesics down. So this is an M gamma. Now we can take pi gamma and we can map them down to M. Okay, and what's going to happen? So here is S cross 0. Okay, so there are two things you need to know. First of all, you need to know that these bounded closed geodesics have to essentially intersect gamma. As curves on the surface, they have to essentially intersect gamma. Okay? If they didn't, there would be some parabolics appearing. So let's ignore that point. If they do all intersect gamma essentially, then if you look at our construction, what's going to happen is the image of these geodesics is all going to have to intersect. They're all going to have to intersect the surface S cross 0. So what we get is infinitely many bounded geodesics intersecting a compact set. Okay, so this can happen.
Can you say like another sentence about that last? Why do they have to hit S cross 0?
Well, let's go back to Kurt's comment. So this, if I look, well, not exactly Kurt's comment, but if I look at the pre-image of S cross 0 in W, it is going to, if I cross S cross 0, I have to cross that pre-image. So this wedge is in here, and if I look at this pre-image, this is going to be, it's going to look like annuli in that wedge also. And so if I cross S cross 0, I have to essentially cross those annuli, which is the pre-image of S cross 0, so down here I have to intersect.
Yeah, you say the intersection issue, say the intersection part of the argument.
Okay, so the first thing you need to notice, the first thing you need to show, is that these curves going out the end have to, these curves going out the end, they're homotopic to curves on the surface. And those curves have to eventually intersect the original curve gamma. Because if they didn't,
It means intersect on the surface.
on the surface,
Project on the
yeah,
surface.
they have to intersect on the surface, they have to intersect gamma Because if they didn't, you could show that there was a cusp in the original manifold. There was a cusp disjoint from gamma in the original manifold. And we've assumed that away. Okay, so now we know that the curves have.
What's the idea for that?
What's the idea for that? So one idea for that is that if you have a bunch of curves, let's say they're all disjoint from some curve beta, so then you can realize the pleated surface through beta in all those curves. Okay. So that tells you, I mean, if you can, so that tells you that there are a lot of bounded length curves near beta. So beta has to be arbitrarily short. There's no upper bounded length in beta, so it has to be a constant.
Because they're far away from beta.
So, yeah, so if you, I mean, so a pleated surface has bounded diameter, well, modulo the thin part, right? So if you have infinitely many curves disjoint from beta, they're all going to be uniformly close to beta, at least the Margulis for beta in the manifold. And that tells you that the Margulis for beta has to be really big. In fact, has to be arbitrarily big, which means beta has to be big. Okay, and so then we know that these curves have to essentially cross they have to essentially cross gamma, and that means that they're bounded length curves. They can't go around this way. So that they have to cross this wedge, and this wedge is going to be separated by a preimage of s cross 0. I mean, what does the preimage of s cross 0 look like in W? I mean, it looks like an annulus. It is an annulus. And that annulus, I mean, is going to be... Okay, so...
I was feeling it had to be geometric because it's just big exponential growing again.
Yeah, that is the reason it has to be geometric finite, but yeah, it has to. So, yeah, but I mean, that's the reason why three manifolds should fiber over the circular hyperbolic too. So, yeah, if there's something you have to do, right? I mean, you need to worry that this wedge could stay uniformly thin, right? I mean, how do you have to.
I mean, doesn't you know that the wedge, the injectivity radius in the wedge goes to infinity? So,
How?
I have a picture of
but you
it.
have, I mean, it's just,
What?
it's just a question of H.
So- Yes, but the boundary of that annulus so the boundary of that annulus at infinity could be dense.
So I return to my question, what does geometrically finite mean?
Yeah, I was gonna answer that one. Not letting me. By the way, this is great. I've been really looking forward to having this talk with you asking us the questions. So. What? Yeah. Did I answer your question?
You may be less sure of my question.
Yeah, so if you look, we have no control really of the geometry of this annulus. This is purely a topological construction. So if you look at, I mean, it could be that when you took the, well, it's a little easy, yeah. It could be in general that the boundary of this annulus was a sphere filling curve. Or a torus filling curve.
You drew your picture as if it was a hyperbolic plane with a geodesic remove in the blackboard number 4 bottom. So
No, that's a topological picture.
Yeah, so make it squiggly.
Okay.
Terribly squiggly.
There we go, yeah.
Yeah, terribly. Well, as you say, if you accumulate on the whole
It's a topological picture, so it was already terribly squiggly.
So,
Yeah, I mean, yeah, so maybe okay, so let me answer Kurt's question. So what do you get in the end? So in the end, what the picture looks like is that what this three manifold looks like is that there is going to be a convex surface facing up, and there'll be this cone singularity somewhere inside. So using this sort of voltage theory, at least, you get that there has to be, a convex core for this geometrically finite manifold. So just like in the non-singular case, the boundary of this convex core will be some convex surface pointing up, and then the complement will be foliated by these level surfaces, just like Dick described.
First question then.
What?
How about the first question?
Yeah, this is the definition of geometry finite in this case, that there is a convex surface cutting off the end, facing up. That's the definition. So the other thing to notice is that so here we are sitting in M gamma, we have this nice convex surface. This convex surface will map down to a locally convex surface in the original free manifold. And so I call this construction grafting, and the reason why is just like grafting up projector structures. So if you know what projector structures are, there is this Thurston classification way of describing projector structures by associating them to locally convex surfaces. And this was, this was a main motivation for doing this construction also, is that, you knew from this you knew from this grafting construction that there were lots of locally convex structures sitting inside hyperbolic free manifolds that weren't embedded. And this is a way of making them embedded. Oh, and the other comment I wanted to make, that this is like the covering theorem. This is like the Thurston-Canary covering theorem. It's the same idea is used to prove that. And this is essentially just another version. Okay, well now we have a hyperbolic cone-manifold. Okay, so what do we do next? We check how much time we have left.
Does this imply in particular that when you take the course and cut along the boundary of the sandals, then you actually have control over the modules?
Say it again.
Does this imply that, it's not too moving? You said, oh, it could be a torus filling current, but now you're proving that, look how nice the end is. Does that mean that actually there's control over the modules?
So, probably depends on, I'm not sure. So, you can do this, so you can do, you can do this construction in various settings. So, for example, you can do it in the setting where your original manifold had one degenerate end. And in that case, you can't get the sphere filling curve. Okay? But you can also do it when it's doubly degenerate. I'm not sure, and in that case, you may well. I don't know that we're ruling out that I don't know that we're ruling out the annulus having this being a torus filling curve by proving that it's geometry finite. So I don't know that you could get control over the modulus. Okay. So let's now use this construction to give a proof of the density conjecture in a special case. Okay, so again, so let's assume, so we have rho, again with no cusps, and I have the m rho, which is H3 modulo the group. This is homeomorphic to S cross R, and I want to assume that there is one, let's call it convex end, and one geometrically infinite end. And I want to make one final assumption, and that is I want to assume that the injectivity radius of m rho is equal to 0. In particular, there are points where the injectivity radius of a manifold is just the infimum of the injectivity radius of all the points. And I want to assume that this injectivity radius goes to 0. A gray eraser. Where's that?
Be careful, it's still alive.
It's still alive. I don't know what that means, but I'll be careful. Okay. So let's do the proof in this case, and then I'll make some more comments, and then I'll probably be out of time. All right, so what do we do? So this condition tells us that that there exists geodesics, closed geodesics, gamma I in M rho with the length of the gamma I going to 0. Okay, so the injectivity radius is going smaller and smaller. We can find shorter and shorter geodesics. Okay, and then we have a result of Otal. And what the result of Otal says is that if you have a curve that's sufficiently short, it's unknotted. In particular, it's isotopic to a surface in the product structure. And furthermore, I mean, this isn't super important for what we're doing. Furthermore, if you have infinitely many of them, you can make them all lie on different, you can isotop them. You can isotop the union of them so that they all lie on level surfaces. So we may have to throw out some of them and reorder them, but let's just say that the gamma I are equal to gamma I cross I in M for some choice of product structure on the manifold.
So they always exit on the geometry of the infinite.
Yes, they have to exit on the geometry of infinite N because in the, yeah, that's a good point. So they have to exit on the geometry of infinite N because in the convex N, there are no closed geodesics once you get outside the convex surface. Okay, so Otal tells us we can throw some of them out. We can reorder them so that they lie on level surfaces going up the geometry of infinite N. Okay, so then we apply grafting to get a sequence, to get geometry finite cone-manifolds, n sub I. And let's look at what these manifolds look like. So here is n sub I. And this piece of n sub I is exactly isometric to the original manifold n sub rho. So as I gets further and further out, as I gets bigger, we have bigger and bigger pieces of the cone manifolds that are exactly isometric to the original manifolds. So in some sense, so n sub i's, they converge to M. So for instance, they converge to M in the Gromov-Hausdorff topology, for example. In fact, they converge very strongly. I mean, if you pick a base point over here, and you pick, the approximating maps will be actual isometries in larger and larger complex sets. Okay, but that's not good enough. We don't want to approximate our manifold by cone manifolds. We want to approximate them by actual convex co-compact, smooth hyperbolic manifolds. So what we need to do is we need to apply a deformation theory for cone manifolds that was developed by Hodgson and Kirchhoff. So we want to apply deformation theory for hyperbolic cone manifolds.
You have to leave the category of primary groups. I guess that's a fundamental point.
We already left.
Yeah, we left. Yeah, we went to these cone manifolds.
But now you're using.
Yeah. So yeah, this is another example of another tool that you can use. You have this 3-manifold, and this is an example of another tool that you can use that I guess is not available when you're doing dynamics. So this is due to Hodgson and Kirchhoff. Suddenly spacing out on how to spell Steve's name.
H-O-F-F.
First name, Hodgson.
Hodgson, yeah. Let's write their names neater.
Is Steve the wife of the mistress?
Yeah, so yesterday there was a discussion of having 2 advisors, which I also did, one of who's here, one And the one who was here drove me to the talk today, so we'll just move on. No, my explanation was like having two parents, and you tell one parent that the other said it was okay. That's actually sort of true. Okay. So what this deformation theory allows you to do is it allows you to decrease the cone angle from 4 pi to 2 pi and do it in a way that controls the geometry. So in the end, the new manifold will not have a big chunk that's honest to goodness isometric to the old manifold, but it will be close enough that you can get that the new geometrically finite manifold actually approximates the.
The reason I made this point, I mean, if you do this deformation like this, the dynamics, well, if there were some kind of dynamics and infinity, it would be changing topologically. It wouldn't be like the quasi-conformal deformation.
So, yeah, I mean, you could actually. So I don't know if I actually wanted to say that you could actually produce what the quasi-Fuchsian group should be without doing any of this cone-manifold construction. You can do this whole thing on the sphere in infinity. Okay, anyhow, I think I'm out of time. So maybe I just need to say a few more things. So we made this assumption that the injectivity radius is equal to 0. Well, if the injectivity radius isn't equal to 0, you can do, what's the main point I want to make? So this case is sort of the generic case. So it's a result of McMullen that generically almost all manifolds, in some bare category sense, every manifold has this, almost every manifold has this condition that the injectivity radius equals to 0. So in this method, this case was actually easier. In the ELC method, it's actually easier to prove the ending lamination conjecture if you assume that you have a lower bound on this conjecture here. So the ending lamination conjecture is actually easier to prove if you assume that there is the injectivity radius is bounded away from 0. And so, originally what you could have done is you could have applied this method in this case, and you can apply the ending lamination conjecture techniques in the other case to get a complete proof. But if you want, you could do some covering tricks to prove this theorem in the case when the injectivity radius isn't 0. Anyway, I'm out of time, so I can stop. The whole point of that last discussion that I was supposed to mention your thing. So yeah, you originally proved this in the case when the injectivity radius was bounded away from 0.
Thank you. Any questions?
I wanted to try to repeat that remark again, because if you want to imagine learning from this to prove something on the other side of the dictionary, take the case when the angle is less than 2 pi. Right, and you try to open it up to 2 pi, you go to different angles, so the Fuchsian, or whether the group would change, because the order of the
Right.
So I'm thinking this is like analogous. And then in between, when the angles are not 1 over an inch or pi over an inch or something, the groups are indiscrete.
Right.
So you're leaving the category, the fundamental way of these hyperfinite order symbol classes, which is my feeling why there is this dictionary, discrete groups and rational match are both dynamical systems that are cyclically generated in the order sense. And there's a dynamical sense property that they share. It's not shared by things where you have irrational ellipses. You have subjects to advance. So sort of you're leaving the class of objects in a fundamental way. So that may be something one has to try to carry over. But if you have branching points with some kind of fractional order, instead of having a power, like an energy power, you have some other kind of power that changes the dynamics. I'm just trying to learn from.
Yeah, right. So I mean, if you look at this, these cone manifolds, I guess I wondered, so the total, I mean, first of all, the holonomy is sort of the holonomy, you want to think of the holonomy as being being a manifold in the complement of that curve. And if you do that, in the original 4 pi case, the holonomy is just the holonomy of the original manifold, but it's no longer injective. And I mean, I'm curious as to what happens to if you just look at the bottom half, below the cone singularity, that's just a surface group, and what does the holonomy of that look like? Does it stay discrete? I mean, it could be that it does, I don't know. So it could be that if you just look, when you're doing this cone manifold deformation, if you look at the bottom half, it could be that that bottom half stays discrete. I sort of suspect it doesn't, but...
Oh, it goes to irrational.
No. If you throw away, so you just look at the manifold below the cone singularity. So you cut it off right here, and you just look at that manifold, the holonomy of that manifold. The dot is the singularity. I don't know what that dot is. But that dot, that dot is me doing this probably. Yeah. So you look at so you just get a representation of the surface group there. And that could actually be discrete. I sort of think it is. But.
Okay, so since we are running out of late, I think other questions to the speaker should be private. Let's take him again